All right, we're talking about Rust, which is, if you haven't heard of it, it's a new language being developed primarily by Mozilla, as it did Firefox. So the gist of it is they wanted to make a new browser, so of course they first had to make an entire new language. All right, so just to get a quick example of what the syntax kind of looks like, it's curly braces. It actually looks a lot like the C if you compare here. And being the web guys that they are, they have a little playpen that you can run things online. So I've got a little compiler and it'll run it for me. So I get the output, hello Rust. So that's kind of what it looks like, a quick taste. And the gist of the talk is going to be comparing Rust to a couple more, common languages. And the idea is the trade-off between control and safety. So if you were going to write an operating system, you wouldn't write it in Java. And if you were going to write, well, you still probably wouldn't write it in Java, but there's trade-offs between how safe you consider the language and how much control you get. So here is some C. It may look familiar, it may not, but up here you can see two variable declarations, one A and one B. One of them is right on the stack. So this first one is allocated. Alternatively, you get a stack or a register, and it's called an auto variable. So whenever you declare it, it somehow magically makes a story for you, and then when it goes out of scope, it gets cleaned up for you. But that doesn't always work. Sometimes you need to pass memory around somewhere else. So you can also do heap allocations through malloc for allocating memory. And that's great. So the only problem is that you also have to remember to free everything that you allocate. Otherwise, you leak memory, and then you're taxed on the system at some point. Someone's probably noticed this in Firefox. And then these are great up here. These are good examples of using the facilities to manage memory. Down here are some common bad examples of managing memory and speed. So here, for example, you allocate 1 byte of memory to fit into an integer pointer, which a pointer for an integer will be indexed by 4 bytes instead of 1. So here you aren't allocating enough memory, which is a pretty common. It's not off by 1, but you can also just be off by 1 and it's wrong. Here, allocating another byte, which you don't even assign anywhere. So this is you cannot possibly free this. So you're leaking memory here. Here you're getting the right size, so that's fine, and you're freeing it, so that's great. But then you free it twice, and that's another big no-no. A double free is a big vulnerability. So there you most likely just corrupted a bunch of memory structures that malloc uses to track stuff. And then here you're trying to use memory that you've just freed, which is also it's not yours anymore. Yep.
So how does it become a problem if you allocate a byte of memory that you just don't do anything with? I mean, like aside from wasting that byte of memory, does it lead to other problems?
Yeah. So in 64 bits there's a huge virtual memory space. So you could just have yours floating around somewhere. You wouldn't care. You just keep grabbing up more and more memory. It doesn't matter. Within your process's memory space, you won't run out of memory. But it has to map to physical memory sometimes. So when you're tying it up, another application isn't using that portion of physical memory. So at some point, you're going to exhaust memory here, and you're going to cause problems for the rest of the system. So leaking memory is a bad thing. But
and just for the sake of the video, I forgot this. Just rephrase the question the last one.
Oh yeah. So what would be the problem with allocating memory and then just forgetting? So never using free. If you just allocated memory, you used it, and when you stopped using it, you just didn't tell anyone about it. That would be bad. So that's a common thing to do, though. And the problem is you're either not freeing it at all or you're freeing it twice because you're getting overzealous about when you're going to free. There are ways around this, but that's the gist of it. You have full control, but that also means that you have control to mess things up. And here's another note. Beyond just memory with malloc and free, there's a lot of most common useful structures have some idea of allocation and deallocation. So maybe you open a file, you're supposed to close the file when you're done. When you bind to a socket, you're supposed to close the socket when you're done. If you acquire a lock for shared data structures in a concurrent situation, you're supposed to release the lock when you're done, otherwise you're going to get a deadlock. So it needs to be, everything that you do when you initialize has to be matched by something in deinitialization. So you don't really get that in C. Here, you'll have to usually call some function to get your structure, and you'll have to call some function to deallocate it. So it'll be a common idiom to have a malloc and a free, but for each structure you have. C++ comes along, And one of the big advantages of writing in C++ is objects can have constructors and destructors. So basically, all that means is instead of having to call the free function yourself or the close function when you stop using a file, when it gets destroyed, it can clean up after itself. So it knows how to free itself. That works with auto variables. So if you allocate something on the stack, it knows when it goes out of scope, so it can clean itself up. The problem is that it's not going to work for all of your mallocs and frees still. It's not smart enough to know when you're done using heap allocated memory. So if you malloc something and don't free it, you still don't get this nice, destructor going on. It never happens. So the problem is that C++ has resources, on lock. It's easy to use the API correctly there, but you still have problems with manual memory management. Coming kind of on the opposite, Java has no manual memory management. So everything is garbage collected. If you stop using something and nothing's referencing it, it gets cleaned up for you. But the problem is that that's not deterministic. So there's no way to know when exactly something's going to get cleaned up. So it doesn't usually make sense to have a destructor in Java. So then resources get thrown by the wayside. You don't have RAII. You don't have that auto variable gets cleaned up when it leaves kind of thing. So there's no destructors. So kind of C++ handles the resources and Java handles the memory, and not exactly. Either of them can have problems still, but neither of them handle both. So I think I summarized. Yeah, so if you have full control like C, there's no expectation that your memory's safe, and there's no expectation that your resources are all handled correctly. In C++, you can have some expectation your resources are okay, but memory is still a problem. And in Java, your memory is fine because you aren't handling that yourself, but the resources are still unsafe. And there are hacks to get around this. Java has try. You can do things like in C++ you can use smart pointers now, but it's not enforced, and it's not an idiomatic part of the language. So Rust comes along, and Rust, I would dare say, is safe in terms of memory and resources. So you can get as much control as you like, the same as with C, basically, but you get the safety of C++ and Java. And the way it achieves this is something called ownership and lifetime checking. So in most languages, there's no concept of ownership beyond library types, for example. So like an owned pointer in C++. But at the basic level, the compiler won't check for you whether or not you own something. If you pass it to another function, you don't know if that function freed it. You have to write these in comments. These have to be just understood parts of the API. So the advent of Rust is it will check these things for you at compile time, and you won't have any problems when you run. And the nice thing is it doesn't achieve this through reference counting, but you can get reference counted types for things like concurrency. And it doesn't achieve this through garbage collection, so you can get deterministic deallocation, and they call it drop instead of destructor. So you can get the nice resource safety, and you get all this memory safety. A few other nice things about it. It's immutable. All data structures and all data you allocate is immutable by default. So it's great when you want to do concurrent things. It's always const correct, because the moment you need to start mutating, that's when you say it's mutable now. So it's immutable by default, which is good. And everything is passed by value, so it doesn't hide things like Java, where if you pass a primitive type, it'll copy by value. But if you pass an object, it passes by reference. Everything's passed by value. But there's move semantics, so that's part of the ownership thing. If you don't specify that you're moving by reference, it'll do it by value, and you won't have access to it now. So it can be efficient by just it's same as copying a pointer, but you get all of the same guarantees. So it's still similar to C++. You can have auto variables, so things that are allocated on the stack, and that's what's encouraged. And there's no null pointers, so it's impossible in Rust without really trying. You can use something called unsafe, which I'll describe later. But in idiomatic Rust, there's no such thing as a null pointer. It's a guarantee the compiler checks for you. So you can never dereference a null pointer in Rust. Oh, another quick note. I've heard that this is very similar to Lisp macros, but it doesn't use a preprocessor like C. It uses a hygienic AST manipulating macro system. So you get in basically a set of symbols that represent the code, and you can modify them. And it's hygienic, meaning symbols don't leak. So your references to variables are metasyntactic kind of. They're referring to the variable, not the actual string that represents the name. And beyond just making boilerplate easier to digest, you can do things like check arguments at compile time. So the variadic printf in Rust, it actually checks its types when you compile. So you never get to runtime and printf decides you only passed in 3 arguments, but you asked to print 4 and then it crashes. That never happens. Also, regex, there's a module for regex, and it will compile a nice parser for you in line, right where you declare it. So it doesn't have to compile it at runtime. It compiles it when you compile the rest of the code. So I want to just give a real quick side-by-side. This is some C code that does nothing, but it's kind of a common idiom to have a struct, and then all of your functions that refer to that struct take it possibly as the first argument. You have something to allocate and something to free, and then you can do things with it in the middle, as long as you remember to make a new one and you remember to free it at the end. Oh, I'm missing it over here. This should be the Rust equivalent over here. I don't know what happened there, but I can pull that up at the end. It's the difference is that you define these methods actually on the struct, and you can define a drop so that when it goes out of scope here, deterministically when it goes out of scope, it knows to free it. And so you can do things like files can be cleaning themselves up when it goes out of scope. And this works for even pointer types, because when you move something, it analyzes lifetimes and figures it out. So here's some Rust. You'll notice it's similar to C, but not always. Statements can end with a semicolon, or they cannot in certain cases. But let binds a variable, here a, which is type int. And you don't actually need the int here. It will infer types most of the time, so that's another nice thing. If you want heap allocation, you can use a box. That's basically the equivalent to malloc here. When you say box, it allocates and puts the pointer in here. That's an owned pointer. If you don't do anything with an owned pointer, it just gets freed, because when it goes out of the last its topmost lifetime, when this scope ends, Rust has been analyzing the entire time throughout your program, and it knows that nobody's using it anymore. Without doing any reference counting at runtime, it knows at compile time when you need to deallocate this box. So it gets dropped for you. You don't have to do anything, which is nice. So there's no when you malloc something, you don't have to free it. It gets freed by the compiler deterministically. It knows where to free it. And then trying to parallel those problems that you might have in other languages, here, if you allocate on the heap and then try to drop, so this is equivalent to free, it works once, and then the second time a compiler error will come up. So this doesn't happen at runtime. You don't double free. There's no such thing, because you've already moved value A. So Rust compiler is smart enough to know that once you drop it once, you can't drop it again. And also you can't use it at all. And that's a nice thing here. I'm gonna pull up, if I can real quick. Doing it live. I'm gonna try. Yeah, here we go. So if I just want to find, this is also showing off how nice the documentation is for Rust. There's some really nice, oh, standard library. Nope. Ah, here it is. All right, so if I just wanted to see the interface for drop, it's in std memory, and it's a function called drop that takes a generic type t and then disposes of the value. It can be used destroy any value. So if you look at the source, though, there's an interesting thing about this function. It does nothing. So it's actually defined in pure Rust. This isn't a compiler thing. It's similar to free in that you can call it as any other function, but all it does is take ownership here. So when you pass it in by value, it takes ownership of the value x, and then it does nothing with it. And that's the compiler coming in, and when it sees that nobody's using the value anymore, because I took ownership of it and then did nothing with it and didn't return it, it knows to free it. So all that's happening is it's just basically hinting the compiler to destroy the object here. So that's that'll be in there. It's immortalized. So that's all the drop does. So it's basically all the drop is doing is making this semicolon, this curly brace happen earlier. It's basically limiting the scope by letting another scope take ownership and then drop. And so that's my last little tidbit. This is the important bit to know about Rust is someone owns every object at any given time. There's the idea that you don't have multiple pointers into the same thing that are all mutable. That's impossible. You can't have multiple people owning the same thing. And that gives you nice guarantees about when exactly something needs to be deallocated. And the times when you need to circumvent this are for efficiency. And you can, I don't have any slides here, there's a syntax for unsafe code. So what you do is, let's say, for example, you wanted to move an object between two threads. Instead of having to make a whole copy of it, it would be more efficient if you could atomically take ownership from one into some intermediary and then give ownership to another. And there's the idea of a channel in here. But that's unsafe because you need to take multiple pointers at any given time into the same thing. So what you do is you start an unsafe block within some library function. You do the unsafe thing that the compiler doesn't understand, but that at the end, as long as you guarantee that all of the same invariants hold, that all those safe things still hold, then the compiler can keep going, and it assumes everything's still okay. So you can, there's an escape hatch to get to the level of basically C programming. You can do, if you just wrapped your whole program in unsafe, you could basically write C in Rust, which is the nice thing because you can get all of the great efficiencies that you get in C, but with all the safety that you could possibly imagine. So
wait, so we could write all of our C programs in Rust?
Very close. There would be very few changes if you wanted to. You can write, one thing you can do is you can ask that the standard library that you use contains no allocation, and then you can redefine the start symbol, and then you could run this bare metal as an operating system. So you could write an operating system in Rust. That's the level of systems programming that it's at. And
Did we put it on MSP 130? Oh my god.
I don't know, probably. What's up?
Are we going to get to the dangers of using Rust right now in a bit?
Yeah, so the problem with Rust right now is that it's not 1.0. It's not a stable release. So if you go and you go and look at the GitHub, it's constantly being worked on right now. And the best you can do is pick the latest stable and work with that. But there's no guarantees about any of the API stability. There's no problem. There's no guarantees about the compiler stability. So up until 1.0, all the code that you write in here could be broken tomorrow. So right now, you might want to just toy around with Rust, but probably not write anything too important in it. Yeah.
So if I want to use this, like what dependencies do I need? Will it integrate with an IDE like Eclipse, or how would I go about?
There are projects right now for getting it integrated with things like IntelliJ, which I've never used personally.
Okay.
It works very well. You don't really need, I haven't had any trouble writing it in just Vim, a text editor.
Okay.
It's pretty straightforward. The problem right now is it's so unstable that nobody's really committing to writing a big, a plugin for anything, but people are working on things.
Does it have, like, you know what it's like? Does it have a lot of dependencies? Like, I mean, is
It depends.
for embedded devices, or?
It depends, I think, basically solely on LLVM. That's
Okay.
what the back end is when it compiles it down. So anything that LLVM targets, they're trying to target, I think. And
Okay.
also, right now, you can get binary versions of it, so you don't need anything you don't need to compile it right now. You could just get the latest stable. I think they do nightly builds. But if you were going to run it on, an embedded device, you'd have to get the whole tool chain set up. But I think it's
Okay.
basically just LLVM. And it's written in Rust. So the compiler itself is written in Rust, Bootstrap. So you can get one binary compiler and then bootstrap yourself and start
So then
writing.
maybe for an embedded device, you're better off to recompile the whole thing with LVM, Clang, and then just eliminate GCC from the mix. I don't know. I'm thinking that maybe.
Well, it doesn't use a C compiler. It doesn't use Clang or like GCC, I don't believe. You have to compile LLVM first. So
But I'm saying
you'll use
maybe
that.
if you were going to do this on an embedded device, you could compile everything with Clang, and then you wouldn't have GCC. You see what I'm saying? You'd use Clang for everything for Rust, and for you use LLVM for your Clang, and then LLVM for your Rust too. I don't know. I'm just thinking. I don't know.
But I'm just saying Rust is written in Rust, so you can't use Clang or
Oh, so it's because I thought you were saying it uses LLVM, but you're saying it compiles to that language. Okay.
it compiles to LLVM intermediate, and then I use
Okay.
LLVM to get the final bytecode. So
Okay. I see what you're saying.
it targets LLVM, so then from LLVM you can target anything. But
Oh, okay.
the compiler itself that emits LLVM intermediate stuff is written in Rust. So you have to bootstrap it with a binary version of it. But you can write, I think there's targets for a few different embedded devices. And there's some really nice projects, like one called Nickel, where you can use a macro to describe the platform you're on. So you don't have to write boilerplate, for example, for registering all of your callbacks, the vector for the interrupts and things like that, and ports and things like that. You can define all the registers and things. So there's some nice projects for embedded things. I'm still not sure how stable all that is right now, but by the time 1.0 comes out, it'll probably be pretty attractive for that. So that's about all I had. If anyone has, yeah, I can. I'm not sure where. I think I just lost it by now. I was changing it a little bit, and then I think I just completely lost it. But
Well, thanks for taking the time to put it together. It's a good presentation.
thank you.
Lots of good information.
Yeah, I think it's just gone. I mean, if anyone's interested, it'd be taking a while. But if anyone's interested in seeing more what it looks like, maybe after the talk, we can just like run through writing some quick stuff with it. If anyone's actually interested, but the syntax isn't the difficult part. The concepts that it introduces are the more difficult things. But so that's all I have. Any other questions?
Any more questions for Stringy? What's up, Artis?
Yet another programming language to choose from.
I went over my head. So, but it doesn't use a runtime environment, right? It
No.
compiles it for.
There's a very
Can you
minimal.
repeat the question to me?
Oh. Yeah, so it is asking if it uses any runtime. So there's very little in terms of runtime. If you ask, there's a very small one, but if you ask, you can get absolutely none. And you
No,
can
I mean, I know Java uses a runtime environment, so it runs your program within a program.
no, this compiles down to the bytecode. This is
Oh.
all at the processor level. It doesn't depend on any, even within that. Some languages will still have a small runtime. You can ask for absolutely nothing, so you can run it on an embedded device. You can ask for example, there's a standard library version that has no allocation, dynamic, or anything like a malloc equivalent. So you wouldn't even have to implement malloc on an embedded device. You could just run it.
Don't most devices though have something that'll take C code and convert it to the byted code?
You mean a C compiler?
A C compiler, basically.
Yeah, but you'd need a Rust compiler to
Right.
compile
so
this. But
do they have one for every processor then?
it uses LLVM.
I don't know what that is. So
Okay,
maybe
well that's
what
basically you
LLVM
can,
is.
if you target LLVM bytecode, you can compile that, or I don't know what they call it, assemble that into any of the things that LLVM targets. But
then you would need a processor that's LLVM compatible.
no, LLVM targets the processor. So I see what you mean. You would need one that LLVM targets. But there are LLVM targets for plenty, I'm pretty sure. So you can target anything LLVM targets with Rust,
So
I believe.
LLVM is like an intermediary between
Yes.
C and the C compiler and the bytecode.
Not just a C compiler.
Or the
But
Rust
there are
compiler.
C compilers. Clang was written against LLVM. That's a C compiler that targets LLVM. Rust is also Rust C, the Rust compiler, targets LLVM in the same way that Clang does. So
Oh, okay.
basically, anything that Clang supports, Rust
GCC
supports.
used.
It emits immediately, I believe.
Oh.
It has its own tool chains for stuff. But
Anything else for Stringy?
I have one.
Yeah.
So are there objects on Rust?
I didn't actually have it on the slide, but oh, are there objects in Rust? So there's a similar concept to objects, just that you have struct, and it's laid out very similar to C. So you'll have struct packing in this way. If you had two ints here that both took up 4 bytes, let's say, then this whole object here would be represented exactly as 8 bytes. I believe that's exactly how it works in Rust. So you would just do struct.
So they have
Oh, it's not working.
So they have structs, but not objects.
You can define methods on a.
Oh, you can define methods.
You
within
can- you
a
can
Rust
use-
struct?
Hmm?
Can you define Rust methods within a struct?
You don't so much define it within the struct. What you do is you define the struct as just the memory layout of the struct
Okay.
and all the fields. You define also whether or not there's data hiding. So you define whether or not it's private by default, and then you can make areas of it public to things outside of the module. And then you do implementations for various traits. So you can implement just on that struct all the things that struct alone can do. And then you can implement traits. So that's basically an interface. So there might be a trait for whether or not it can be printed. It's called show, I believe. So if you can printf it, then you would implement show for it. And the nice thing is, actually, you can have the compiler implement it for most things. So you can say, do a generic, whatever you do to show all the things that are in part of this, show mine as an amalgamation of all of those, or things like that.
So basically, object methods are just normal methods that apply to structs.
They're just a nice like syntactic sugar on calling a function with that as the first argument, basically. But so it's almost like C, but you get the nice object-oriented kind of syntax for it, if I understand it correctly. And then there's traits to do interfaces. But the cool thing to understand is that the struct itself is represented exactly basically as it is in C. It's packed the same way almost. So you get a good interface to C, actually. You can talk back and forth with C very well. It has a good FFI with C. So if you had existing C code, you could write Rust against it pretty easily. Yeah.
We love you, Stringy.
Hey.